In this video, we're going to look at finding derivatives using difference quotients. So the definition of a derivative that I have boxed here, you may recognize from previous sections and previous homeworks that we've done. It's the same definition that we've always been concerned with, but in those previous problems, we've been dealing with evaluating the derivative at a specific x value. What we're going to start doing now and moving forward for the most part is we're going to evaluate the derivative in a general sense. So when we do that, we don't replace our x value with something and evaluate it. We just evaluate f prime of x. We treat it as a function of x, and we treat both of these variables as variables. There's no value attached to them until we make it so. So what I mean by that is once we evaluate the limit as h approaches 0 at some point, we treat those as zeros. But we treat these x's as the variable that affects our function. So what we also have is we have an equivalent form for finding a derivative, and it's namely, it looks like this. What I'm going to do for this video is focus on the definition that we know, but then I'll kind of talk through this process of using the equivalent form of the definition of the derivative. It won't be a long drawn out work shown for it, but you'll kind of see how it works. So what we're doing in this video is we're determining the values of x for which the tangent of f of x is horizontal for f of x, this rational function that we have here. So part one, and kind of being given to us in the way that it is with the question, kind of gives it away what we're doing. The first part of it is to find the derivative, because what we're talking about is we're wanting to find whatever x values make the tangent of f of x horizontal. Whenever we say a line is horizontal, say something like this is our axes, we have this line right here. With a horizontal line, what we have is a slope of 0. So we're going to keep this in mind. We want to set our slope equal to 0 somehow. What that entails for us to do in this process is we know that the derivative gives us slopes of tangent lines of f of x at any given point. But what we're going to do is first going to find the derivative in its general sense, so find the derivative of this function as a whole, and then find out what happens when we set the derivative equal to 0, because the derivative is our slope, so we're setting it equal to 0, and then we're going to solve for x values that make that statement true, that make our derivative equal to 0. Okay? And so since we're doing the whole derivative, slope of a tangent line, slope of a curve process that are equivalent, what we're going to need to do is, again, analyze our function a little bit. But what we did in previous videos is we would check for discrepancies, which we really don't need to worry about here, because when we checked for those discrepancies, we wanted to make sure we weren't evaluating, say, this function at x equals -3 specifically, because if we did that, we'd get an undefined value there. What we're doing now is we're taking the derivative in a general sense. So if the function is not defined at x equals -3, the derivative is not going to have a value at x equals -3. So we don't really need to worry about where the asymptotes are and all that kind of stuff like we did in previous videos when we were evaluating specific values, because when we do it in a general sense, if it's not defined in the function, it also won't be defined in the derivative. So what we're going to do for these problems is just jump straight into finding the derivative. Okay, so we're going to use the definition, like I said, that's in the box. So we have f prime of x is the limit as h approaches 0 of f of x plus h. So we're going to change f of x to f of x plus h. So this is going to give us x plus h squared over x plus h plus 3. And then we're going to subtract f of x. So we're just going to rewrite the function that we were given, x squared over x plus 3. And this is all going to be over h. With a quick mental pass to the limit test, we know that if we plug in 0 for h, we're going to get x squared over x plus 3 minus x squared over x plus 3, so 0 in the numerator, and we get a 0 in the denominator. So this returns an indeterminate form. So what we do at this point is we go ahead and move forward with manipulating our function inside of the limit a little bit and seeing if that can more easily make our limit apparent to us. So we have the limit as h approaches 0. The first thing that I want to do is I want to try to expand this binomial here, because we have x plus h squared. So that's x plus h times x plus h, or that gives us x squared plus 2xh plus h squared. And this is all still going to be over the same denominator that we had from before. And then the second fraction is not going to change. We can't really expand that in any form or fashion. and then we have all this is over h. Once we get here, there's nothing we can really do inside these fractions individually, so why don't we combine them into one fraction? Okay, that seems simple enough. So what we need to do for that is we need to have the same denominator in both fractions. And we can make that happen. It's just going to take a little bit of multiplication. So in our case here, what we're going to do to find our LCD is we're going to multiply the two denominators together. So we have x plus 3 times x plus h plus 3. Okay, so in order for this to be our LCD, we need to figure out what the denominator of each fraction is missing. And in this case, the second fraction is missing an x plus h plus 3 factor. So we're going to multiply the numerator and denominator of it by x plus h plus 3. And then in the first fraction's case, we're missing x plus 3. So we're going to multiply the numerator and denominator of the first fraction by x plus 3. So now let's carry out that multiplication in this next step and see what our function becomes. So the limit as h approaches 0 still. And so what we're going to get is, I'm actually going to write it so where it's all inside of the same fractions, so we're not confused as to what we're doing. So we had this times x plus 3, and this is all going to be over x plus 3 times x plus h plus 3. And this is going to be then minus x squared x plus h plus 3. Close the parentheses off, over x plus 3 times x plus h plus 3. So this is what we're dealing with now in the numerator, and this is all again over h. So in this next step, what I'm going to do is I'm going to take care of the multiplications that I have inside of the numerators of our two fractions. So I'm going to multiply, or I'm going to distribute all these different terms in and take care of this multiplication. So what we have now is the limit as h approaches 0 of x cubed plus 3x squared plus 2x squared h plus 6xh plus h squared x plus 3h squared. And then since these two fractions have the same denominator, what I'm going to do is put them over, or be within the same fraction in this same step here. So we have this common denominator of this that we found, and then we're going to subtract whatever we find to be multiplied here. So we're going to subtract, then we're going to distribute x squared into this parentheses to take care of that distribution. So we get x cubed plus x squared h plus 3x squared. Okay, and this is all over h again. What I'm going to do, instead of making another step, just rewriting all this just so I can distribute that negative in there, once we distribute this negative into this parentheses, every one of these signs is going to change of these different products here. So I'm going to go ahead and take care of that all in this step right here. So what we have is minus x cubed minus x squared h and minus 3x squared. So this is what we're dealing with in the problem right now. This is our function that we found so far. What we're going to go ahead and look for next is in this numerator, this long string of terms that we have here, let's see if we can cancel some stuff out. So here we see an x cubed and we see a minus x cubed. So we can subtract those away because those evaluate to 0. What else can we take care of here? Let's see, we have a 3x squared. We have any other x squared terms. We have a minus 3x squared. Can take away the 3x squared and the minus 3x squared. Those evaluate to 0. 2x squared h and minus x squared h. So that's going to evaluate to just, actually, we need to write the limit as h approaches 0 first. Don't want to forget that. Limit h approaches 0 of, and then we're going to have x squared h, because we have 2x squared h minus an x squared h, so we're left with just 1. So then we're looking for 6xh terms. I don't see any. So we have plus 6xh. And then we have h squared x. Nope. And plus 3h squared. So we've taken care of combining whatever like terms that we can combine, and this is what our numerator looks like now. This is also going to be over that LCD that we found. And this whole fraction is still going to be over h. What I see as I look in these terms of this numerator that I have here is I see that each of these terms has an h in common. Okay, this first term has one h, this one has an h, this one has two h's, and so does this one. So what I'm going to do is, because I know that a step in my immediate future from the processes that we've repeated for this type of problem over and over again, I'm going to end up multiplying this fraction here by the reciprocal of the denominator, namely 1 over h. So if I can get that 1 over h to cancel with an h in this numerator, it makes it easier for us to have to deal with stuff. So let's go ahead and factor that h out of our numerator and see what happens. So we get h times x squared plus 6x plus hx plus 3h. And this is all going to be over still that same LCD that we had right here. And then like we said again, the next step, this is still going to be over h, but what we're going to do is we're going to multiply by the reciprocal of the denominator, doing keep, flip, multiply. So we have 1 over h being multiplied to the numerator and denominator. Cancel out the h's there. The 1's go away arbitrarily. But then this h can divide away with this h because they're both factors of division and multiplication in their own right. So we have the limit, as h approaches 0, of our numerator that's left, x squared plus 6x plus hx plus 3h over x plus 3 times x plus h plus 3. So now that I've gotten to this step, I really don't see anything else that I can do to simplify this function that we have. So what I'm going to do now is I'm going to pass the limit and plug in 0 for h to see if I can evaluate to find my derivative, namely a function that we can have. So what I'm going to do is everywhere I see an h, I'm going to plug in a 0. So we have x squared plus 6x plus 0 times x plus 3 times 0. So we know 3 times 0 evaluates to 0, 0 times x evaluates to 0. So that worked out really nice. We're left with an x squared plus 6x up there. We have an x plus 3. That's left alone. There's no h in there. But then we have x plus 0 plus 3. Okay, so now let's see what happens with that denominator. The numerator we said was going to remain x squared plus 6x. But now we have x plus 3 times x plus 3. So we can condense those down, make it easier on ourselves by saying x plus 3 squared. So what we found here is our derivative for this function that we were given. So like I said, this is the method and the approach to using the limit as h approaches 0 definition that we have. We were also given an equivalent form for this question in the limit as z approaches x of f of z minus f of x over z minus x. What this function that we're evaluating the limit of, what this is going to look like is we're going to evaluate, instead of f of x, f of z. So we'd have z squared over z plus 3 minus x squared over x plus 3 over z minus x. So for the most part, the process of evaluating that's an indeterminate form, getting an LCD to combine the fractions, doing the multiplication and the canceling of terms, it's all going to follow rather similarly, but it's going to look different because we're dealing with f of z and f of x. So it's largely the same steps, it's just going to look different. You're still going to need to combine these fractions, cancel out terms whatever you can, and then there's going to be a key part, kind of like what we had here with factoring out the h's. In this process, you're going to end up kind of doing something with maybe factoring a cubic or factoring something along the lines that ends up having you cancel out this z minus x in the denominator in some form or fashion, or divide it away because they're both parts of the same division. So I'm not going to go through and write out that step, but if you would like to see that and you think that process is simpler, you are more than welcome to use it, because like we said, these are equivalent forms of each other. We can use either one of them and obtain the same answer. So now I'm going to scroll back down here, and now we have found the derivative, but we need to talk about part 2 of our question. In part 2 of our question, we're concerned with now finding the values of x where the tangent of our function is horizontal. So what we've done is, in part 1, we found the derivative for our function, and how we're going to find the values of x where tangent is horizontal is we're going to use the derivative. But like we said earlier, when a line is said to be horizontal, its slope is 0. And we view the derivative as the instantaneous rate of change, or the instantaneous slope of our function. So what this means that we're going to do for this process is we're going to evaluate f prime of x equals 0 and find what x values make this statement true. So here we have the derivative, which was x squared plus 6x over x plus 3 squared, and we want to figure out where that equals 0. Remember how earlier we talked about if the function's not defined there, the derivative won't be defined there? Well, there's a good illustration of this right here. Because the derivative is defined such that our denominator is x plus 3 squared, if we plug in negative 3 here, we're still going to get a value of 0 in our denominator, making our derivative undefined. So this just goes to show that wherever our function is not defined, our derivative won't be defined either, because there's no slope, there's no curve to take the slope of, and there's no way that we can find out the instantaneous rate of change at that point if there's no graph or there's no value to take that derivative of. So what we're going to do is when we're solving for x like this, we know that in this situation, we're really only concerned with finding out where the numerator is 0, right? Because what happens here is we can multiply away this x plus 3 squared to both sides, and it cancels out here, and then 0 times that is just 0. So if we were to multiply x plus 3 squared to both sides, and I can't even really fit it in over here, but I'm going to try x plus 3 squared like that, it cancels out over here. So what we're really concerned with now, wow, that was horrible. There we go. So what we're concerned with now is the statement x squared plus 6x equals 0. So what we're going to do here is we know that if when we have a statement like this equals 0, we can factor out and we can take an x out of both of these terms. So we get x times x plus 6 equals 0. We're using the zero product property there. So once we've done that, we know that we can set this factor equal to 0 as well as this one and solve for x. When we set that first factor equal to 0, we get a value. We get x equals 0. So now we need to figure out what makes that second factor equal to 0, so we solve for x, and we get x equals negative 6. So what this means and what we found is we found that at x equals 0 and at x equals negative 6, the tangent line of our graph of our f of x is going to have a horizontal slope or a slope of 0.